Starting. All right, we are starting, gentlemen. Okay, today is the normal approximation to a binomial. Okay, so a normal approximation to a binomial distribution. A binomial distribution can be approximated by a normal distribution with the same mean and the same standard deviation. Thus, a binomial distribution, which we shorten to this, binomial n comma p, can be approximated by the normal distribution. So we use n for normal distribution, np comma npq. And q is obviously still 1 minus p. NP is what? In our formulas that we learned last lesson. NP is the mean, it's the mu. And NPQ is variance, so it's the standard deviation squared. So it can also be written like this one down here. So that means that the normal distribution with the numbers, the mu and the variance in there. When approximating, we treat the discrete binomial variable x as if it were a continuous normal variable. Okay, remember binomial was discrete data, whole numbers, that's all we could do. But on a normal distribution curve, it's a continuous scale. You can have whatever decimal number you like in there. Okay, for small values of n, we have to apply a continuity correction. Now, what is a small value of n, you ask? Well, that's a bit debatable, but definitely things under 100. Large quantities would be things in the thousands, okay, where you may not need the continuity correction, but we'll see that in one of the examples that we're going to do. So hopefully the question will indicate, if it's a bit vague, whether you should use the continuity correction or not. So this means that you're going to be finding half the interval corresponding to the boundaries of the cumulative frequency histogram. So for example, if we were trying to find the probability of 8, 9, 10, 11, 12, and we're treating the x as being on a continuous scale, we would do half a unit below the 8, which is 7.5, to half a unit above the 12. So we're going to be looking between 7.5 and 12.5. So that's what we mean by a continuity correction. That's what you'll need to do. So a rule of thumb for using the normal approximation. For a fixed number of n Bernoulli trials, the normal approximation to a Bernoulli distribution is less satisfactory when the distribution is skewed, okay, because it doesn't work as well. For a fixed probability p, the normal distribution to a binomial distribution, there's too many distribution words in here, is more satisfactory when the number has a large number of trials. And a common rule of thumb, one amongst many, for using the normal approximation to a binomial distribution, it is required that the NP, which is the mu, the mean, is greater than 5. NQ being the same if we're using a half, greater than 5. Okay? All right, let's have a look. Questions. Oh, before the questions. You will need to have a table, because when you're using the normal distribution, normal approximations, actually before we move on, can you just write down here, because it's not on your booklet, but I wrote it down last lesson for you, and you need it even more today. To calculate a z-score, it is z equals x minus mu over the standard deviation. Okay, because to change between our x scores, we're going to have to change them into z scores to use our normal distributions, and that's going to come to our table. Yeah, Ben?
Are we given this?
Yes, you'll be given at least a portion of it if you're required to use it, yes. Yeah, the portion that matters, correct. So there is a way to calculate it, and I have put on our Google Classroom a video link that if you will have this model of calculator, then you are able to actually approximate it on here, but that's just out of curiosity. Oh, you have one too. The other models don't do it. It has to be the 100. But you will always be given the table, so you don't need to do it, but it's just if you want to have a look at that later. There's a video, you can watch that later. Okay, so this table, and the tables are all a bit different as well. So this table is different to the one in your textbook, which may be different to the one that you're given in the HSC. You don't know, okay? They can do it differently. This table is actually very thorough because it gives you 3 different options of which part of the normal distribution that you would like, and that makes it easier to use. The one in the textbook, I believe, always tells you from the left-hand side to your Z-score. It always does everything to the left of your Z-score. So you've got to try and manipulate your results to get what you want. Okay, but we'll use this one today for our examples. Skip over all that. We'll be coming back to it. Here's a big table, big table, big table. Here they are.
Yeah. With this table, if the shaded we're trying to find out it's in the negative area, would that mean when we try to figure it out, would we get a negative answer or would it be the same answer as if it was?
So the cool thing about the normal distribution is that it's symmetrical, right? Yeah. So if you've got your center of your data where your mean is, if you were trying to find, say, 1 standard deviation above, or whatever your Z-score is above up here, that space there is identical to that space there, one the same space below, like if it was 1 centimeter below. So the area would be the same, that's right. Okay? All right. But we will hopefully see that in our practice. All right, question 1. A coin is tossed 20 times, phones away, and X is the number of heads. Find the probability that the number of heads is greater than 12, and we're going to do it with a binomial distribution first, and then we're going to approximate it using our normal curve, our normal distribution curve. Okay, so binomial distribution, if we have 20 coins or 20 tosses of the coin, that's our N. The probability of getting a head is going to be a half, which means that Q is also going to be a half. The probability of getting greater than 12 heads, does that include 12? No. So in other words, we want at least 13. 13 would be the minimum number we could have. So probability of 13, probability of 14, all the way up to 20. I'm just going to go dot, 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 all the way up to probability of 20. So that's a little bit painful, but we can do it. To find the probability of 13 heads, we would go 20C13, half to the power of 13 and half to the power of 7. The good news is that it's always going to be half to the power of 20, which will make this faster. I'm not going to do all of them. I'll do the next one though. 20C14, half to the power of 14, half to the power of 6. And we get our pattern happening, and it would go all the way up to 20C20, half to the power of 20. To make it a little bit easier to calculate, because there is quite a few of them in there, each one of those probabilities is going to have half to the power of 20, because the 13 plus 7 is 20 and 14 plus 6 is 20. It's always half to the power of 20. And it's really just the combination at the front that is going to give us a different number at the front to multiply by. So let's put those into a set of brackets. We would have 20C13, 20C14, 20C15, 20C16, all the way up to 20C20, and type that into your calculator. You'd have to do all the ones in between. You won't be able to skip any on your calculator. Do you want to try it? Or are we pretty confident we can do that and we can just move on?
It's 20C20 just
20C20 will be 1. 1, 3, 2, is it, to 3 decimal places?
Yeah.
Very good. Okay, so doable, but a little bit of a pain when there is so many different probabilities that we're adding together there. Okay, and that's not even really a lot. You can get so many more than that. What if there was 100? What if there was thousands? Okay, so using the normal distribution is an excellent way of approximating things when you have a lot of different probabilities that you want to do. So let's do the same question using normal approximation now. Let's first of all practice. No. This is our notation for our normal approximation. The NP, remember, is the mean. How do you find the mean? You times the N times the P. There is 20 for N and P is still a half. What is 20 times a half? 10. So my mean is 10. NPQ, multiply them together. 20 times half is 5. So remember that this is my mean, this is my variance, so standard deviation squared. Okay, so if we are finding our normal approximation, we want the probability when our score is greater than, was 12, wasn't it? Yep, greater than 12. But what we discovered was that it actually had to be 13 or bigger, right? Because it couldn't be equal to 12. But remember I talked about something called a continuity correction. Because I'm now going from discrete data into a continuous scale, there's only 20 scores in this thing. This is quite a small number that we're using here. We need to use a continuity correction. So I'm going to change this to be that x is greater than or equal to, what is it going to be? 12.5. You do half a unit below. Okay. All right. Now I want to change this into a Z score because my tables use Z scores. So our Z score formula, I'll do it over here on the side, is x minus mu over standard deviation. My score, my x, is 12.5. I subtract off my mean, which is 10, and I divide by my standard deviation. Well, my variance was 5, so my standard deviation is going to be square root of 5. No, not 0.5, it'll be 2 point something or other, square root of 5. Okay, you type that in your calculator, and you should get 1.18. However, in our table that we have, if you look back a page, all of those decimal numbers are rounded to 2 decimal places for that table. So I can only do 2 decimal places. So I'm going to round that to 1.12. Okay, so a score of x being greater than 12.5 is the same as a z score of greater than 1.12. Approximately. This is an approximate, so you could put an approximately equal to sign on there. Well, we have to work that out now. Let's go back to our table. So let's go to our table. We want 1.12. Page 11. 1.12. I'm going to bring that there so I can see the table, the little normal graphs below. So 1.12 means I've got a curve. Okay, 1.12, so the middle is in here, so we're going to say 0 in the center. 1.12 is going to be something above it, right? I'm wanting everything greater than that. Is that one of the options in my, look down the bottom here? So the smaller portion. If I find the smaller portion of 1.12, 1.12 is here. The smaller portion should be the, oops, that might be my highlighter, should be this middle one. Because I'll go back up, come up here. So you see the smaller portion was the middle one? So it is 1.1314. Okay, does that make sense how I did that? So that would be if I wanted to know from my mean, which is in the center, to my z score, I wanted that part in there. Okay, so it's going to depend on the question. You're going to have to be flexible. They are still rounded, and you will find there can be small differences from table to table or to your calculator if you're getting your calculator to do it. But this is 4 decimal places, so it's, yep.
The exact answer.
Okay, so where was my question? There. Okay. So this is equal to 0.1314. That is the probability. Done, finished. Let's do another one. Question 2. Tossing a coin 20 times, and X is the number of heads. That sounds familiar. Find the probability of the number of heads is within when it's within 1 standard deviation of the mean. So it starts off the same way. We still have N equals 20. We still have P is equal to 1/2, and Q would also be equal to 1/2. But this time we're talking about scores that are 1 standard deviation from the mean. So I have to find out what those scores are that are 1 standard deviation from the mean. I'm going to need to know what the mean is. Actually, we already know that. So it's the same as last question. What was my mean? It was 10. What was my standard deviation? It was 5. The variance was 5. So it was root 5 for the standard deviation, because this was the same as the last question. But if I want to find the probability of scores that are 1 standard deviation from the mean, if my mean is 10, I need to go 1 standard deviation down. So in your calculator, you're going to type in 10 minus root 5. And we get, correct, 7.76. That'll do for now. And then I want 1 standard deviation above, which means I want to do 10 plus root 5. 12.24 to 2 decimal places. Okay. Now, this first one that I'm doing here is meant to be using the binomial distribution. Binomial being discrete, whole numbers only. So I'm actually finding the probability of whole numbers that are bigger than 7.76. So that would be 8, 9, 10, 11, and 12, but not above 12 because I can't get above 12.24. Yes? Discrete for binomial. So then we have the long process again, which is why we start to lose favor with binomial distribution, of doing this the long way with our formula. So it will be 20C8 half to the power of 8 and half to the power of 12. I'm going to shorten it. 20C9, just going to shorten the half to the power of 20 every time. And so on. You would do all of those all the way up to 20C12 half to the power of 20. To shorten that slightly, to type it into your calculator, bring the half to the power of 20 at the front like we did last time, and type in 20C8 plus 20C9 plus 20C10, and so, actually, there's only 20C11, I might as well write them all. I do. Okay, so that's all of them in there. And you get 0.737 to 3 decimal places. Okay, let's see how close it is if we use our normal approximation. Are we ready? People are still writing? Okay, normal approximation. Our n is still 10,5. That was the same as before. We are trying to find the probability of, now we were finding up here 8, 9, 10, 11, 12. Oh dear, I just deleted things. Let's go back. No, oh, there we go. Okay, in here, in the binomial, 8, 9, 10, 11, 12 were the ones we were finding. So using my continuous scale, what am I going to find between? Correct. So 7.5, between 7.5 and 12.5. half below, half below my lowest value, half above my highest value. So I need to find the Z scores for each of those. Let's do them underneath. You might end up just doing this part in your calculator at some stage, but I'll write the calculation down. So Z score is going to be, for the first one, 7.5 minus my standard deviation, my score, sorry, over my mean, over my standard deviation, which is square root of 5. So it is X value minus the mean over the standard deviation. That's our formula. Equals.
Why couldn't
Which is same as last time, but anyway, there it is. Minus 1.12. And if we do the other one, our Z score is going to be 12.5 minus 10 over square root of 5, which is the positive 1.12. So graphically, what this means is here is my normal distribution, my mean here in the middle, my one standard deviation above and one standard deviation below, and I'm trying to find that part in there. Okay. I'm going to do my table, but before I do that, I need to write down my probability as a Z score. So probability is going to be a Z score between minus 1.12 to positive 1.12. Now, think about the three sections. I don't want to redraw that graph. The three sections that we've got on the table. Probably going to be easiest if I find the mean to my Z score and I just double it because it'd be symmetrical. It's the same on the other side, right? So let's go back to our table. 1.12, where's my 1.12 again? Because it was the same number as the last one. Here's my 1.12, but this time I want the mean to the Z score, which means I'm going to use that one. Yeah, the green one. Does that make sense? So, slowly scrolling through all my tables. It is approximately 2 lots of 0.3686, which is 0.7372. How close is that? The first one was 0.737 and very, very close. So that continuity correction actually made a really, really close answer. Okay, question 3. This is the bigger one. Oh, the part C. Oh, there is a part C. Comment on the results of this calculation. Oh, I think all we want to say in there is that they're both giving us the same thing. It didn't matter whether we used the binomial or the normal distribution, we were getting the exact same result. So both methods give the same result. Yeah. Well, okay, one of them I rounded to 3 decimal places. Never actually kept that fourth one. See how close it was. But pretty much, when you're talking about probability, that's pretty much exactly the same. Question 3. You freaked out? Oh, okay. So, those symbols have been changed. Sorry, they should be less than signs. Yes. Okay, so this is obviously a very large sample. We have pollster asks a sample. What is that? A pollster asks a sample of 10,000 people whether they intend to vote for the Working Together Party in the next election. The WTP, which is Working Together Party, won 1/3 of the vote in the last election. Using the assumption that this will be the case in the next election, he wants to know the probability that the survey will give him a result within 3,300 people to 3,400. Using binomial probability, the calculation would be yuck. This is a horrible calculation. Imagine if all 25 million Australians were surveyed, it would be a huge, horrible calculation, which is exactly why we can't always use binomial, and the normal approximation is simpler. So it says compute the probability between 3,300 and 3,400 in the question above. First of all, we're going to ignore the continuity correction. So what have we got? N is 10,000. It tells us the probability of 1/3 of people voting for them. That's the probability someone will vote for them, and which means the Q is 2/3. I'm going to have to find z-scores here, so I need to know my mean, which is 10,000 times 1/3, which is 3,333.33 repeater, or a third. I also need to know my standard deviation, which is square root of NPQ, which is 10,000 times 1/3 times 2/3, and that is 47.14. Okay, so ignoring the continuity correction, I just need to change these numbers into z-scores. So we don't really have a lot of room there for formula, but maybe I'll put the first one over here on the side. The z-score would be 3,300 minus the mean, which was 3,333.33 repeater, over my standard deviation. And I calculated that, and hopefully Ben's getting the same thing, as negative 0.71 to 2 decimal places. Okay, so do the same. All you have to do is change the 3,300 to 3,400 to get the other z-score that we need. And we'll be looking for a probability of our z-scores between negative 0.71 z-score and 1.41. Okay, so not so symmetrical on my bell curve. How can we find that? Yes. So let's go back. We need 0. You do the z-score again. I just didn't have room to write it. You just change the 3,300 to be 3,400 for the second number, and you get that second number there. Okay. All right, let's go to our table. I need 0.71. Okay, minus 0.2 back here. So maybe I should draw it. Okay, so if I've got, here's my curve, and I've got my mean in the middle, I've got a negative 0.71 there, and I've got a positive 1.41 here. So I need that part of the curve, and I need that part of the curve. What would be easier to do is consider that negative 0.71 to be just the positive 0.1. Just for, you can only do, there's only positive values in this table, right? So if you just find 0.71 and I want it to the mean, where's my 0.71? 0.71, where are you there? So it will be, to the mean is the first column, isn't it? Yes, so 0.71 should be that one. I want 0.2611 and 1.42 to the mean. I need to write that down. I'm going to scroll it. I've got 0.2611 and then back to 1.42. 1.42 to the mean is that one. So it's 0.4222. So hopefully, if I add those two numbers way back down here, you guys are lucky you don't have to do all this scrolling around. Oh, there it is finally. It should be 0.2611 plus 0.4222. Does that give me the same answer as I've got on there? So 0.26.
0.683 again.
Oh,
Yeah, it's 0.4207.
did I read the wrong number off, did I?
Yeah.
Oh, it's 207, was it? 4207. Does that fix it? Yes, that is what I had before. Good. So it is 0.6818 was the answer. Read the wrong number up. Sorry about that. Yeah. 1.41. Yeah. Oh, I did 1.42, did I? Too much scrolling. I look on the paper.
And then minus of the.
Oh, yeah. So if you did a larger portion, you did the larger portion for both of them? No. No, because the minus one would tell you the upper side, because it'll always tell you that a larger portion, which is on the other side if it was the larger portion. The one in your textbook, though, because it always does to the left, that would work for that one. Yeah. So there's other ways you can do it. There is definitely other ways you can do it. I did it in here differently. I actually did all of them to the center and I minus off 0.5. So I did it differently again. So yes, as long as you're calculating, you could use different, because you've got all those three options, you could do them different ways.
And then
That table doesn't always do to the left though. The larger portion is the larger portion. So if you've got your negative 0.7, whatever it was, the larger portion is actually the right side. It doesn't just do the left side, it tells you the larger portion, which is different. Whereas if you have a different table that does always to the left, then it would work to just subtract those, whatever the 1.4. Yeah. Okay, all right. Now we want to redo this question using the continuity correction, which means if we were doing between 3,300 and 3,400, we have to find the probability half a unit smaller, so 3299.5, so that's half lower, and half higher, that's what we're hoping to find, and it won't make much difference. Okay? And then you turn each of those into Z scores again. So you got your Z score. I'm not going to write the formula out. There's not a lot of space here. But you do 3,299.5 minus the 3,333.33 over your standard deviation, which is 47.14. So it's that one. It's this one over here on the right. We're using that formula again. We're just putting a different number in here for our score. Okay? You should get, has anyone done the first one? Yeah, good. Negative 0.72. So it's only a very small difference, obviously. And yes, 1.42. Okay, so then we go back to our table again. I'm not going to scroll. You guys can find them. Oh, tell me again. 0. Yeah. And does that add to give 0. Oh, good job. Look at that. Okay, so they're close. They're exactly the same to two decimal places. It's only the third and fourth decimal places that are slightly different. So is the continuity correction? Yeah, true. But is the continuity correction doing much there? Not really, no. So yeah. So for the comment part, I wrote down, since the third decimal place is mostly irrelevant, the results are basically the same. So since the third decimal place is mostly irrelevant, the results are basically the same. Cool. So this is why for large for large values of n, you can ignore the continuity correction because it doesn't make much difference at all to your z-scores and hence to your result. Yeah? Okay, so one more little part to do here. Question 4. I want to approximate 100C53, which we could definitely do on our calculator. We will do it on our calculator as a check. But we want to approximate it using the normal approximation to a binomial distribution B100 half. Check how good the approximation is. I'm going to check it on the calculator at the end. Okay? So, to do it as a binomial, we have B of 100, a half. This is my n, this is the p in the binomial, which is the same as what we've been doing for the other couple of questions. If I was to find the probability when x was equal to 53, now I'm choosing 53 because if I use my binomial formula, it would be 100C53 half to the power of 53 and half to the power of 47, or in other words, half to the power of 100. And here is the 100C53 that I'm trying to approximate. Okay? So if I can find the probability of x is equal to 53, and I just have to divide it by the half to the power of 100, I've found an approximation for my 100C53. I don't know why we're not doing the calculator, but it told me to do this, so I'm doing this. Okay, so if I'm down to 100 scores again, so continuity correction time. If I'm looking at x is equal to 53, then I'm changing this into z scores. I'm going to do half below 53 would be 53.2, and half above 53 would be 53.5. So anything between those two things would be considered a score of 53. I need to know my mean and my standard deviation so that I can turn those into z scores. My mean is, 100 times a half, which is 50. And my standard deviation is the square root of 100 times a half, which is 5. Yeah? So using the z-score formula yet again, not going to write it down, but the z-score formula, you put in your score, 52.5. It's if it was variance, it would be squared, and I put the square root over, so I just want the standard deviation. So you put in as a fraction, 52.5 minus the 50 all over 5. That's how you work out the z-score. What do you get? Correct.
Just check on the calculator.
Did you do the whole top as a fraction? Yeah.
Yeah, it's because 0.5 is the double times.
So half of 100 is 50. Half of 50 is 25. You got to do the square root goes. Sorry, my square root should go over the whole thing. Is that where the problem is? You got to do everything. The square root is over everything. That's what's messing everyone. Okay, now I get what's going on. All right. So now we're up to our Z scores. Go to your table, please. Now, because these are both, we have they're both on the same side of the mean, right? We have. Here is my rough little sketch. Mean is over here, and we have a 0.5 and 0.7 would be slightly above that. If you can read off going to the mean, if you find to the mean of 0.7 and minus 0.5, that would be the answer that you wanted. So read off on your table, please. Find the 0.7. and find me the measurement that goes to the mean. What is it? Somebody other than Ben, because I know he knows how to do it. Come on, we got. Oh, I can't. I have to do it. The bell's about to go. Ugh. It should be 0.7580. Did you find that? And then you minus 0.6915. And you get 0.0665. That should be a 0, sorry, messy. Okay, that is not the answer because remember, we are trying to find an approximation for 100C53. Remember back here at the beginning, I said 100C53 would be approximately equal to the probability of 53, which I worked out was the 0.0665. That's what all that working out was for. And I just have to divide by the half to the power of 100 to move it across the other side. Yes. Oh no. It's had a stressful day. You should get 8.43 times 10 to the 28. Now that was a whole lot of work. What does the calculator type it in? If you just type in 100C53 on your calculator, what do you get? Oi, anyone awake out there? You get 8.441 times 10 to the 28.
So that all that working out was just to replace what C is.
Yeah, it was just another way to approximate it using the normal distribution.
Why didn't we do that? I don't see the purpose of that.